All right, so we're going to have a look at this finite difference scheme. We're going to derive the values of the coefficients A, B, and C. It's a 3-point scheme for the second derivative, and it's a forward scheme. So we're using points to the right of 0 to try and determine the coefficients. All right, so with all of these, what we do is we assume that we know, and we're trying to approximate the second derivative at this point here, at the start point. What we want to do is we want to use Taylor series to express the values of f1 and f2 in terms of stuff we know at naught. So that's what we're going to do. We're going to figure out the Taylor series for f. So f of x equals, so it's the Taylor series of f at this x naught location, if you like, right? So we're going to expand around x naught. So that's x minus x naught, first derivative of x at f at x naught, plus second derivative term, right? And then there's higher order terms onwards, right? So I guess I should also note that f naught is equal to f of x naught. So let's use this to determine what f1 is, right? So f1 is at point 1, where we've gone x equals x naught plus h, right? So that's f of x, that's f of naught, plus x is now x naught plus h minus x naught. That leaves us plus h. Oops, that's a naught. Plus h squared on 2 double dash plus higher order. So now we want to go x naught plus 2h. Right, so that just comes from substituting into our Taylor series, like so. So now what we can do is we can plug in our Taylor series into our finite difference scheme, right? This is just a supposition, yes? We've assumed that we can approximate f double prime at naught by this sum, and we just have to find the appropriate coefficients a, b, and c. So we plug our Taylor series in. Oops, that should be an equal sign. So f1 is this now. I'm going to drop the third order terms. We know that they're there, but that's what we're going to neglect. See. Okay. So now we just group up the like terms. like so. Now we can equate like terms across the equal sign. So on the left-hand side of the equation, we have no f naught term. So the only way that this equation can be true is if a plus b plus c equals 0. That gets rid of the f naught term on the right-hand side. Now, we've got to get rid of this f prime term as well. That necessitates bh plus ch equals 0. 2ch, sorry. Obviously that h cancels out, right, because h is non-zero, and we've got b plus 2c equals 0. Our final equation is actually one where we can equate the f prime terms. We've got one f double prime on this side. We've got bh squared on 2 plus 2ch squared on this side. So we have like so. These are the three equations for our three unknowns, a, b, and c, that we have to satisfy. So the easiest way to approach this problem is to use the information from this, namely b equals minus 2c. We can plug that information into this equation here, and we'll get a value for c. Alrighty. Okay, so we've found c. Back substituting into the equation above gives us b. And now we can substitute values for c and b into our first equation. A plus b plus c equals 0. So our a is equal to in this case, a equals c, which is kind of nice. So our overall finite difference scheme is and you can trace back what size of error that we've made by looking at what the size of the term that we've neglected is. You can check this on Wikipedia. The coefficients are correct, so you can actually go and plug in. So you can go and look up the tabulated version, which will be 1 minus 2, 1.